Hello everyone, welcome back to my channel InfoSec Lab. It's the second day of TryHackMe's AI security learning path, and today we're diving into AI models and data. This room explores how data is fundamental to AI security and which models power it. Without further ado, let's get started. Introduction. Every AI model is at its core a product of its training data. Before a single prediction is made or a single prompt is answered, decisions about what data to collect, where to collect it from, and how to process it have already shaped everything the model will ever do. Those decisions carry security implications that most organizations deploying AI today have ever examined. From PII script from the open web to credentials baked into the model weights to safety mechanisms quietly eroded during the fine-tuning. The risks don't begin when a model is deployed. They begin long before, in a data supply chain that is often invisible, poorly documented, and almost entirely unaudited. The learning objectives of the room is to understand where AI training data comes from and the security risks introduced by poor data provenance. Recognize how the PII and the sensitive credentials can become permanently embedded in model weights through the large-scale web scraping. Understand how the key model building decisions like overfitting, quantization, and federated learning each introduce distinct security risks. Understand the inheritance problem and what organizations unknowingly tag on when fine-tuning pre-trained models. Recognize why trained models are black boxes and what models are to address this. Training data. In the AI ML security threads, we talk about the machine learning lifecycle and establish that before a model can be trained, data must be collected and cleaned. That sounds orderly enough, but let's slow down and ask questions that the lifecycle diagram doesn't answer. Training a large language model requires a staggering amount of text. GPT-3 was trained on roughly 570 gigabytes of future text, and that's considered relatively modest by modern standards. To hit numbers like that, developers can carefully handpick sources. The pipeline typically draws from 4 buckets. First is web scraping. What is it? It's automated crawls of public internet content like news, forums, blogs, social media. The trust profile, which is the trust level, is low because there's no curator, no version control, and the content changes after collections, so it's not very reliable. Licensed datasets. Data purchased or agree with platforms like OpenAI plus Reddit, Meta owns social posts. The trust profile is medium, terms often unclear, original user rarely consented to AI training use. Synthetic data. AI generated content used to train for the AI system. The trust profile is a little bit variable, growing fast. About 12% of fine-tuning datasets now contain LLM-generated content, and internal corporate company knowledge bases support transcripts, clinical notes used for the fine-tuning. Now for the trust profile, it's a little bit higher because organizations has direct control, but also direct liability if mishandled. The most widely used training dataset is Common Crawl, a free, publicly available archive of web crawl data that has underpinned essentially every major model family. DeepSeek version 2 will be trained on this. DeepSeek version 3 trained on the 14.8 trillion tokens worth Common Crawl as a core source. And LLaMA4 was scaled to 40 trillion tokens across 200 languages using similar pipeline. GPT-3 is one of the few models whose breakdown is publicly documented. 60% of its token came from the future version of Common Crawl. And more recent models lean even more heavily on it. The keyword is filter. And how that filtering was done, by whom, and what's lived through is where the security story begins. The problems of provenance. Data provenance is the ability to answer 3 questions about any piece of training data. Where did it come from? When was it collected? Has it been modified since? The honest answer to all 3 is we don't fully know. Most major models are essentially trained on datasets of datasets, huge corpuses assembled from hundreds of upstream sources, where the original attribution has been lost, simplified, or never recorded in the first place. The Data Provenance Initiative audited over 1,800 datasets and found that more than 70% of licenses on popular hosting platforms were listed unspecified. On hosting platforms were listed as unspecified, and of those that were labeled, 66% were miscategorized, usually listed as more permissive than they usually are. Organizations fine-tuning on these datasets often don't know what they legally have, let alone what's actually inside. The software security world has been here before. SolarWinds taught the industry that you can't trust a compile binary if you don't know what went into it. which is exactly why software bills of material becomes a standard practice. The AI equivalent of the ML boom are documented inventory of dataset sources, licenses, PII categories, and filtering decisions. Adoption is still early, and most organizations deploying third-party models today have nothing closer to one. PII in the pipeline. One of the most direct consequences of undocumented large-scale web scraping is that personally identifiable information ends up baked into the model weights. Once it's there, it's very difficult to remove. Medical records, personal email threads, forum posts about health conditions, or political views. All of it gets wrapped up if it was publicly accessible at correct time. The EU's GDPR explicitly requires data minimization, meaning collect only what's necessary. The security implication is measured as concrete. Truthful Security scanned the December 2024 Common Core archive, which is about 400 terabytes of data from 2.67 billion web pages, and found nearly 12,000 live verified API keys and passwords. With the right prompt, a model trained on that data can sometimes be caused into surfacing training content near verbatim, including credentials. This isn't a bug introduced by an attacker, it's a consequence of what went in during training, and no patch fixes it once the model is deployed. A model's behavior is a direct product of what it was trained on. If that data was scraped without audit, contaminated with PII, or manipulated upstream, those characteristics become part of the model, and there's no reliable way for the organizations deploying it to know. The data supply chain is as real and as exploitable as software supply chain. For organizations right now, it's almost entirely invisible. Answer the question. What term describes the ability to answer where data came from, whether it was collected, and whether it has been modified? That's data provenance. What is the name of the most widely used public corpus that underpins essentially every major model family? Common Core. What is the AI equivalent of a software bill of materials, or SBOM, used to document dataset sources, licenses, and filtering decision? The ML boom. Okay. Building the model. When we cover the ML lifecycle, we did so at a high level, data in, model out. This task zooms into some of the decisions made along the way that have yet to be covered. Each concept below establishes a foundations for future security topic. So the goal here is not just to define them, but to understand why they matter from a security perspective. Epochs and overfitting. An epoch is one complete pass of the training algorithm through the entire datasets. In practice, models are trained on over many epochs. The algorithm repeatedly sees the same data, adjusting its parameters each time until it converges on accurate predictions. The catch is that more epochs don't always mean a better model. Train for too long, and the model stops learning general patterns and starts memorizing training data specifically. A problem called overfitting. An overfit model performs well on its training data, but poorly on other data. This matters for security because overfitting is one mechanism by which a model can memorize specific details from its training datasets, including sensitive ones, making it more likely to reproduce them when prompted. Model validation. To catch overfitting early, a portion of the training data is held back and never used for training. This is the validation set. At regular intervals during training, the model is tested on unseen data to check whether its performance is actually generalizing or just improving on the training example it's seen before. If training accuracy keeps climbing, but validation accuracy plateaus or drops, that's overfitting in real time. From a security perspective, validation is the quality gauge in a machine learning lifecycle. A model that skips throughout the validation is one whose real-world behavior is unknown, and such unknown behavior is a security risk. It also means that any biases or anomalies introduced through the compromised training data may go undetected until the model is already deployed. Post-training optimizations, pruning, and quantization. Once a model is trained, it often goes through compression steps before deployment. Two of the most common are pruning and quantizations. Pruning means removing parameters that contribute little to predictions, shrinking the model size. For the security consideration, changes in the model behavior post-training rarely documented in detail. Quantization reduces the numerical precision of weights, for example 32 bits to 8-bit floats, to cut memory and compute requirements. This can decrease safety aligned with the behavior. Backdoor defenses tests on the full precision model may fail to detect threats in quantized versions. Both steps are applied after the training is complete, often by a different third-party team packaging the model for distribution. Research has shown that quantization can silently degrade the safety mechanisms built into the model. Defenses that worked on a full precision version might fail to detect backdoors once the model is compressed. When an organization downloads a quantized model without documentation of what changed during the compression, they inherit unknown behavior modifications alongside efficiency gains. Federated learning. All the training approaches covered so far assume that data flows into a single central location for model training. Federated learning flips this. The model is trained across many decentralized devices or organizations, with each participant training locally on their own data and only sending weight updates back to a central server for aggregation. This was designed with privacy in mind. A hospital sharing patient records to train the model is data protection the problem. A hospital contributing model updates without ever sending the record is a much easier conversation. In that sense, federated learning genuinely does reduce privacy risk at data level. The security trade-off, however, is that the integrity of the training process becomes much harder to verify. In a centralized setup, the organization trains the model controls the data. In a federated setup, participants can submit poison local updates, and these can be very difficult to detect at aggregation state. The question shifts from who controls the data to who controls the aggregation, and can any participant corrupt it? Federated learning is therefore an interesting case study in security trade-off. It solves one trust problem by distributing control, but in doing so creates another different one. Answer the question. What term describes one complete path of the training algorithm through the entire dataset? Epoch. What problem occurs when a model memorizes training data rather than learning general pattern? Overfitting. What post-training optimization technique reduces the numerical precision of model weights to cut memory and compute requirements? That's quantization. What training approach trains a model across decentralized devices, sending only weight updates rather than raw data to central server? Federated learning. The inheritance problem. Training an LLM from scratch means assembling trillions of tokens of data, acquiring the compute infrastructure to process it, and running a training job that costs tens of millions of dollars. For most organizations, that's not a realistic option. Instead, the dominant model for AI development today is start with someone else's work. Pre-trained models and fine-tuning. A pre-trained model is one that has already been trained on large general-purpose datasets. These base models learn broad language understanding, grammar, facts, reasoning patterns, and world knowledge. They're produced by a small number of well-resourced organizations and then made available for others to build on, whether through open weights or through API access. Fine-tuning is the process of continuing to train one of these pre-trained models on a smaller, task-specific dataset. A healthcare company might fine-tune a base model trained on clinical documentation to improve its understanding of medical terminology. A law firm might fine-tune on case law. The result is a model with the broad capabilities of base model, now specialized for a particular domain or use case. So what fine-tuning changes? The model's task-specific behavior, tone, and domain knowledge. What fine-tune does not change, the base model weights. The inheritance problem. This is where security concern sits. When you fine-tune a pre-trained model, you inherit everything that model already contains. This includes things you cannot see or did not choose. Biases baked during the pre-training process. Unexpected behaviors introduced by the base model's training data carried through. Any safety alignment built into the base model is not as durable as it may appear. This shows up in three concrete ways. Safety alignments erodes, not breaks. Stanford and Princeton found that the defense mechanisms of aligned LLMs can be compromised by fine-tuning only as few as 10 adversarially crafted examples. Even benign fine-tuning on legitimate data degrades safety as a side effect. Think of safety alignment like a well-worn path through a forest. The model has been trained to follow this safe path when generated responses. Fine-tune is like adding new paths through the same forest. Even if those paths are legitimate, they can gradually obscure the original path. The model hasn't forgotten how to be unsafe. The probability weights have just shifted, making unsafe responses more likely again. The defense mechanisms don't snap, they wear down. Specializations increases attack surface. Cisco found out that fine-tuned models are measurably more susceptible to prompt injection than the base models that were fine-tuned on. The reason is structural. Fine-tuning narrows the focus, reducing resilience to unexpected tokens. Think of it like this: a model fine-tuned on financial records gets better at financial reasoning, but also becomes more responsive to an attacker who frames the prompt in financial terms. Versions matters, and it's rarely tracked. Fine-tuning always targets a specific checkpoint of the base model. If the checkpoint later turned out to contain a backdoor or problematic training data, every derivative inherits it, regardless of whether anyone downstream was told. Without knowing exactly which version of model was fine-tuned from, there's no way to assess that exposure after the fact. Inheritance tax. When your organizations deploy a fine-tuned model, you're not deploying the fine-tuned work your team did. You're deploying the entire pre-trained base beneath it. That base was shaped by training process you didn't control, on data you didn't audit, by an organization whose supply chain you almost certainly haven't reviewed. Fine-tuning is powerful, but it doesn't sanitize what came before it. Answer the question: what is the process of taking a pre-trained model and continue to train on a smaller task-specific datasets? Fine-tuning. What term describes a model that has been trained on a large general-purpose dataset? Pre-trained model. The black box problem. Models are the black box. When a security team wants to audit a piece of software, they have options. Source code is readable. Even compiled binaries can be disassembled, stepped through, and reasoned about. A trained model's weights are neither. The billions of floating points numbers, and they carry no human readable record of how the world is shaped, what data influence them, or what behaviors they encode. You cannot open a model and find the decisions that makes it behave a certain way. This is a black box in the truest sense. This means trusting a model is fundamentally trusting the process of producing it. You can test its behavior, run inputs through that, benchmark it against known tasks, and probe it with adversary prompts through red teaming. All of these are valuable, but they're sampling, not auditing. They can tell you how the model behaves on the inputs you drive. They cannot tell you what it will do on inputs you haven't thought of yet. The attack surface is defined by the model's training, which is opaque. Model cards. The documentation's artifact designed to address this is the model card, a structured document that accompanies a model and describes what it is, how it was built, and where it falls short. The concept was introduced by the Google researcher in 2019 and has since become the closest thing in the industry that has a standard transparency format. A well-formed model card should give you the answers to the questions you can't get by inspecting the weights themselves. Training data. It tells you what sources were used, how they were filtered, the known gaps or biases. Intended use. It tells you what the model was designed for and explicitly what it wasn't. Evaluation results tell you the performance metric across different conditions and demographics. The known limitations tells you the conditions under which the model is known to underperform or behave unexpectedly. Bias assessment tells you where training data or evaluation may have introduced skew. And the lessons lets you know what you're legally permitted to do with the model. The gap. Have you ever checked out a food label and all sounds good until you find out your chicken slices are only 45% chicken? In practice, model cards can also be frequently incomplete, vague, and absent entirely. Unlike food labels, there's no regulatory requirement to produce one, as of now. It remains voluntary for most use cases. The incentive to be thorough is weak when disclosing limitations might reduce adoptions. The Data Provenance initiatives audit over 1,800 datasets, found documentation gaps throughout the AI supply chain, and model cards at the end of that same undocumented pipelines. From a security standpoint, A sparse or missing model card isn't an inconvenience, it's a warning sign. It means the organization distributing the model either didn't evaluate it thoroughly to document the findings or chose not to share what they found. Either way, the downstream user is flying blind. From a security standpoint, a sparse or missing model card isn't an inconvenience, it's a warning sign. It means the organization distributing the model didn't evaluate it thoroughly enough to document findings or chose not to share what they found. Either way, the downstream user is flying blind. In short, the model card is your audit trail. In the absence of one, there's no audit trail, just a black box and the hope that whoever built it was thorough. In security, hope is not control. Answer the question, what documentation artifact accompanies a model to describe what it is, how it was built, and what are the foreshots? Model card. What are the billions of floating point numbers that make up a trained model collectively referred to as weights? Alright, enough with the theory, let's go to practical lab. So this is a simulated model repository built to resemble Hugging Face, one of the most widely used platforms for hosting and sharing open source AI models. Because anyone can upload a model, it's a powerful resource and real supply chain risk. Your job is to perform a model audit. Think of it as scavenger hunt for red flags, the warning signs that a security conscious engineer should never ignore. They could be lurking in the model card, the metadata, the file listings, or the training details. After you submit your findings, you'll get feedback on each one, learning the severity and significance of each issue as you go by. By the end, you'll have practical checklists for evaluating any third-party model before it gets near a production system. Introduction. You're a security analyst. Your team has been tasked to evaluate whether the following one is safe to integrate into the internal tooling. Complete a security review for the model card and flag any concern before sign-off. Your task: read through the model card, files, and sidebar details carefully. Hover over suspicious text to reveal hotspots. Click them to flag findings and rate the severity. Okay, let's begin audit. Enterprise Classifier version 2. A text classification model designed for enterprise document routing and categorizations, fine-tuned from Enterprise Base 1.1. This model classifies incoming documents into organizational categories such as support tickets, procurement requests, compliance queries, and internal communications, built for integrations into automatic document processing pipelines. How to use form transformer. So this is how to use. Training data. Model trained on data curated from the publicly available web sources, including forums, Q&A sites, and public documentation. The training corpus was assembled to cover a broad range of enterprise communication styles and domain-specific terminology. Approximately 1.2 million text samples were used across the classification categories. Training procedure. Fine-tuned from Enterprise Base 1.1. Using standard cross-entropy loss. Training ran over 8 epochs. Training ran for 8 epochs with a learning rate of 2 times 10 to the negative fifth, which is 0.00002. And a batch size of 32. Early stopping was applied based on training loss convergence. The final model checkpoint was selected as epoch 7. Intended use: document routing. Automatically classify and route incoming enterprise documents to the appropriate department of workflow. Support triage. Categorize support tickets by type or urgency to streamline response to pipelines. Compliance filtering. Flag documents that may require compliance review based on content classification. Internal communication. Sort and tag internal messages for archival and search indexing. Evaluation. Evaluated on a held-out test set of 10,000 samples. The model achieved a remarkable average of F1 score of 0.91 across all classifications categorizations. License listed. Flag is fine. License listed with custom with no link, no terms, and no contract, and no contact detail beyond the organization name. I would say high, because we don't know anything else about the organizations that produces this, which is a high security risk. Okay, what else? Go to the file. We have the README file, JSON. What is it? The LFS. Enterprise classifier version 2 LFS. What? The model file size is significantly smaller than the base model, with no documentation of what post-training modifications were applied. Okay. Configure JSON. Enterprise classifier. The model size is significantly smaller than the base model, with no documentations of what post-training modifications were applied. What was the model? Downloads. License custom enterprise 1.1. Where do I find that? I will put it high. I put it high because we didn't have a lot of information about the organizations that train this model. On top of that, this model is fine-tuned based on the model version 1.1, meaning that we didn't have enough information about the pre-trained base model. We didn't have any information about what changes on the version 2, and hence it can inherit securities from the first model, and with the fine-tuning it can introduce more security risk in the second model. So that's why I put it high. Organizations, model, license, base. This is the base model. 1.1 enterprise tags. Why is it not verified? How to use? Okay, this is another flag. Okay, hold on. This is another flag. Publicly available web sources. It's okay, I think it's low because we don't know a lot about what sources it collected. It's from public, so remember the trust profile is low. If you scroll up over here, training the data. When you collect data from publicly available sources, the trust profile is low, meaning there's no curator, no version control. The content changes after the collection, so we don't know the accuracies of that. You know, I put medium. Fine-tune for enterprise base 1.1. A specific version with no documentation of what version contains and whether it has no issue. Again, as I explained, because we didn't have anything about this version 1.1, I will put it high, approximately 400 megabytes. Standard cross entropy training on Epochs. Start web buys on training loss proven convergence. Classify routing. Support tickets by streamlined pipelines. Flag documents that may require compliance review based on content classification. Internal should this one be highlighted because it's not verified? License, custom, base model, enterprise 1.1, tag, text classification, enterprise. Oh, we have 2 more to go for. README, can't read it. Config JSON, token JSON, tokenization configurations, model starts. What else do we have? We have 2 more. Let's go to the lab. Warning signs that security conscious. The file listing of the training details. The metadata, the file listing of the training details. There's nothing here. Text classification, enterprise. Enterprise, a text classification model designed for enterprise documenting the routing custom. There's nothing here. Classifier pipeline text classification trusted model AI. There's nothing here. Model trained on career public, including forum, QA sites. Put it low because it's publicly available. Any information can be changed. No mention of PI filtering despite script forums and web data in the corpus. I'll put medium because even though some personal identifier information was disclosed, it wasn't that serious when it comes to security risk. To cover a broad range of enterprise communication style DOM. Training apply at 32. Epic. Document automate classify and route incoming enterprises. This is hard. On a hard level of 10,000. Yeah, I don't know what this is. No bias evaluation, no limitation section, and a sparse value evaluation section with no adversary or red teaming testing documentation. So as it has been explained, even with the red teaming testing, you only test what happens with the red teaming input. You still don't know what the model behaves or how the model behaves or what the red team hasn't thought of. And because of that, we don't know if there are any other severe security risks out there on the surface of the model. Because of that, it's like a complete black box for me, for us. So that's why I put a high risk security and then add it to audit. Now we have 6 audits. Let's submit it. Oh no, we have 0 correct. That is bad. Okay, let's try again. Enterprise documentations baseline model. Training data sources fake. No provenance collected or checksum provided. Well, but how do we determine the severity? Like, I would say everything is medium and above. But I don't know, forum QA sites, it relates to personal information, so high. The enterprise base 1.1, fine-tune from enterprise 1.1, fine-tune from enterprise 1.1 specific version with no documentations of what that version contains or whether it has known issues. Well, it comes to the point where we mentioned that not a lot of companies adopt to provide the model cards, so it can be something that the company doesn't want to do or doesn't keep in mind of doing. So I just like put it low. I don't know. Documentations automatic. No bias evaluation, no limitation sections, no sparse evaluation section for adversary teaming. I put it high, it wasn't correct, so I'm medium. This one nothing, low. Model size significantly smaller than the base model with no documentations of what post-training modification were applied. Low. I don't know. Okay, we got 2 correct out of 6. I put this one high. I was wrong. Okay. This one should be high. Fine-tune from enterprise base 101. Acceptable but not the optimal rating. Okay, no bias evaluation. No limitation section sparse on. Okay, training data sources fake, no provenance. Okay, put it high, I guess. Because no provenance, we don't know where the collection data and checksum provided. The training data sources fake. High, okay, with okay, we got everything correct except for this one. Training data sources fake, no provenance collective data. See, it's just a gray area. We don't really know. Like, it can be either medium or high. I say that everything is going to be medium and above, but for some reason, some of those are just low, or there's no low. But yeah, anyways, we got a flag. Alright, so that's it for the room today. In this room, we talked about security risks of AI systems way before they were deployed to productions. We also talked about AI data pipeline, how they are collected and trained by the models. We also learned about many concepts in data training like quantizations, federated learning, fine-tuning, pre-trained models or trained model weights, etc. Everything has their benefits and their trade-offs when it comes to security risk. If you have any question, feel free to reach out to me. I'll be happy to help. With that being said, thank you very much for watching. I'll see you next time. See you.